David's talk today is on climate change and variability in Florida. He will review increasing global trends in greenhouse gas concentrations, how they are impacting the global climate system, and how these trends are manifested in Florida. Following his presentation today, there will be plenty of time for questions and discussion at the end. Everyone should now be muted for the duration of the presentation, but we will be unmuting everyone following the presentation to take questions, and you should have the ability at that time to mute and unmute yourself. And you can also submit your questions in the chat window at any time during the presentation, and we will get to those questions, or as many of them as we can. And I believe that takes care of the housekeeping. David, we can see your presentation, and I think we've tested your audio, so you should be ready to go, and I'll turn it over to you.
Okay, thank you, Emily. Can you hear me fine?
Yes.
Okay, great. And I would just like to take this opportunity to welcome Emily Powell to FSU and COAPS and the Florida Climate Center. She just joined us back in July and is still physically located in Austin, Texas, but we'll be moving to Tallahassee. So we're very glad to have Emily on our team, both with Florida Brace and with FSU COAPS. So with that, Tracy, if you could go ahead to my first slide or my cover slide. I'd like to open with this image. It's a spectacular, actually it's a video capture from about a 5-minute video that's available on YouTube that was shot by some storm chasers in the eye of Hurricane Michael back in 2018. And they're on Highway 98 looking east into Tyndall Air Force Base. And you can see it's a well-defined eye of what was then a Category 5 hurricane. You see sunshine and clear skies in the eye. You can also see the eye wall and the stadium effect structure, which is indicative of a very powerful and mature hurricane. And you can also see the damage to the stand of pine trees there, where nearly every tree is leveled. Growing up in Panama City and still having family and friends there, this one was kind of personal. 2 years later, they're still a long way from recovery from all the impacts from this storm. Another interesting thing with this photo, growing up as a full-fledged weather nerd, I always dreamed of experiencing the eye of a major hurricane. After seeing the devastation, I'm very good just watching the videos from storm chasers. I don't need to be there myself. Okay, with that, we'll go ahead and get into the heart of our discussion on the next slide. We're going to kind of frame this webinar by looking at 6 different key weather or climate threats. And these were identified early on in the Florida Brace project by our partners at the Florida Department of Health. And these threats include drought, wildfires, extreme rainfall and flooding, hurricanes and wind damage and other severe weather, heat stress, and sea level rise. So we're going to examine each of these threats, mostly looking at historical trends and what changes we've seen over the past century and even more recently in these threats, and also go a little bit into what we might expect in the future. Now, I'm going to say something that might shock some of you, is that climate change is not bringing any new weather or climate threats in the foreseeable future. All of these have existed all along, and we as a society have had to deal with these weather and climate threats. Now, that's not to say that climate change can't and isn't changing the nature of these threats, their frequency, their severity. There's a growing body of evidence that is occurring to most, if not all, of these threats. But it's still the same threat we've dealt with all along. And one more bit of background, I'd like to do a simple model for defining risk. And risk can be thought of as the threat or the probability of an event times the exposure. What are the impacts? What are your vulnerability? And it can be represented by this simple graph on the bottom left. And where we'd like to be is the lower left-hand corner, where you have either a low probability of an event or the impact from that event is low. You don't want to be up in the upper right-hand corner. But how do we change our position on that graph? Well, all of the threats that have existed all along and could be their nature changed by climate change, there's very little evidence that any of these threats are actually going to decrease in likelihood. So we're not going to get to that bottom left by reducing the probability of an extreme event. In fact, it's more than likely that the probability of these events is going to increase. So the only way to get over there is by reducing our vulnerability. And over on the right-hand side is kind of an extreme example of this. This shows the devastation from the storm surge of Hurricane Michael at Mexico Beach, where just city blocks were scrubbed clean, except for one structure that looks relatively unscathed. This house was built by an engineer, and it was engineered to nearly twice the building codes and building standards, and was very much hurricane hardened. And that's an example of reducing your vulnerability. Now, I'm not sure it's a workable model for middle and lower income families and those that have lived and worked on the coast for generations. They're not going to be able to adapt in that manner, but it is an example. So the next slide, we'll start taking a look at some of the global trends, and I'm sure we've all seen this before, but it's the famous healing curve, a very accurate measurement of carbon dioxide concentrations in the atmosphere from the top of Mauna Loa in the Hawaiian Islands. And this continuous record goes back into 1954, I believe. And what it shows is a very steady, if not exponential, increase in carbon dioxide concentrations since this record began in 1954. At that time, we were at about 315 parts per million. Now we even reached 415 parts per million back in May, and this rise in carbon dioxide concentrations continues more or less unabated as we go forward. What this graph doesn't show you is there's a much longer time series of carbon dioxide concentration from ice cores collected in Antarctica and Greenland. And with these ice cores, scientists have traced back CO2 levels in the atmosphere nearly 1 million years, which covered half a dozen or more ice ages and warm interglacial periods. Well, from that ice core record, never in the past 1 million years have CO2 concentrations been at the levels they are today. And that goes back very much farther than the advent of human civilization. So this is the grand experiment that we're doing to our atmosphere and our planet. Again, CO2 concentrations higher than ever been measured before in the last 1 million years. On the next slide, at the same time, we also have a record of global average temperature that goes back to 1880 or in some cases even beyond. There are 4 or 5 centers around the world that track this global average temperature, that they use basically the same surface instrument observations and just process them a little bit differently, but they all very much agree with NOAA's rendition here, where we see a steady increase in global average temperature since about 1900, or the start of the industrial age. There is some multi-decadal variability mixed in, but that doesn't negate the underlying increasing trend over the last century or more. Another alarming feature of this graph is that each of the last 5 years have been by far the warmest 5 years in this global record. And actually, I've read that 2020 is now on pace to even break the record set in 2016, where we were under the influence of a very strong El Nino. And Now the Pacific Ocean temperatures have turned cooler than normal. It may or may not develop into a full-fledged La Nina, but at any rate, we don't have the benefit of that extra warming from El Nino, and it's still likely we're going to set the record this year in 2020. On the bottom right is a global look at just where temperatures have increased the most. And as expected, it's over the continental areas and the higher latitudes of North America where there's been the most increase in temperature over the last 100 years or so. And this figure is from the U.S. National Climate Assessment in 2014. Another interesting feature is there's two small spots on the globe that have not warmed. That's the Atlantic Ocean just off the southern tip of Greenland. And scientists think it's from melting of the Greenland ice sheet and also changes to the Atlantic meridional overturning circulation that's causing this persistent coolness south of Greenland. There's also one little pixel located over the southeast United States, where if we had a higher resolution map, it would be even more clear that for most of the 20th century, the southeast United States actually experienced a bit of a cooling trend and went against the global average. This was known as the global warming hole, if you will. As I'll show in the next few slides, this map was dated in 2014. Over the last 5 years or so, we have caught up in a hurry. So on the next slide, we'll take a closer look at temperature trends for the United States and for Florida in particular. And top left is just a map. It shows state by state the historical ranking of temperatures, average temperature for year to date, basically since January 1st. And all the orange states are experiencing their on pace for their top 10 warmest year to date since 1895. Florida, you see, though, is on pace to break the record set in 2016 and have its warmest year on record. This is following a trend that we've seen over the last 5 years. 60 out of the last 63 monthly average temperatures for the state of Florida have all been warmer than normal. Only 3 months in the last 5 years have been cooler than average. This includes the last 28 months in a row, all warmer than normal. And during the last 5 years, we've set monthly temperature records in 7 out of the 12 months. And interestingly, it's overnight minimum temperatures seem to be warming quicker than the daytime high temperatures. And just to show you how extreme the last 5 years are, on the bottom is the temperature record for the state of Florida since 1895, smoothed with the 5-year running mean. And we can see in the last 5 years, we're, what I say, entering a new climate regime for Florida, where we're now running the full 2 degrees Fahrenheit warmer than any other 5-year period the state has experienced since 1895. So on the next slide, we'll see that this isn't just confined to Florida either. It's the entire southeast United States. Everywhere on this map where it's shaded dark red, the last 5-year period has been the warmest 5-year period on record since 1895. So it's not just the state of Florida, it's the entire southeast that's experiencing this warming in recent years. On the next slide, we'll take a closer look at overnight temperatures. And what I have here is a plot of the climate division in North Florida, Climate Division 2, where there's a lot of row crops and agriculture. And I show overnight minimum temperatures during the summer months, June, July, and August, again, since 1895. And you can see that since about 1980, there's been a very sharp and steady increase in these overnight temperatures. And the photo on the left is of a not very healthy peanut field in North Florida. In the past 3 or so years, peanut yields have been less than expected in North Florida and South Georgia. And rainfall's not to blame. they've been seeing it in irrigated fields along with non-irrigated fields. So some plant physiologists are thinking it's these overnight temperatures that are keeping soil temperatures high and really impacting the physiology of the developing plants. Some other impacts from these warm overnight temperatures, there's a cumulative stress on livestock and people and human health for that matter, when the body does not have sufficient recovery time at night. There's cumulative stress that can lead to heat-related illness and stroke. So that's kind of what's going on with our overnight temperatures. On the next slide, we'll delve into the idea of urban heat island effect, which certainly we all are familiar with. It's a real thing that the city centers where there's a lot of asphalt and concrete that holds the heat overnight, these urban centers are warming more than the surrounding rural landscape. But this is a very interesting study from Marshall Shepard at University of Georgia a few years ago. We used to think of urban heat island as really the city centers or maybe where the weather station is located at the airport, and there's been a lot of development around the weather station. Well, this study by Marshall Shepard shows that it's urban and even suburban sprawl also contributes over a much broader area than previously thought. So kind of a landmark study there. And interestingly enough, the metropolitan area of Southeast Florida is the urban center that was most affected in this study, other than any other city in the United States, where he determined that 1 to 1.5 degrees Celsius of extra warming occurred in this area due to this urban heat island effect. On the next slide, we'll switch gears and start taking a look at a different threat, and that is for heavy rainfall and precipitation. This just shows last year, 2019, was a very wet year across much of the United States. The darker green states are all ranked as having their top 10 wettest year on record, where all those in the very dark green had their wettest year on record up in the upper Midwest and the Corn Belt. So Oregon was the only state that had significantly less than normal rainfall in 2019. But on the next slide, we'll see that finding any trends in rainfall is very difficult, either monthly or seasonally, just because of the tremendous year-to-year variability. And here I have a graph of warm season rainfall, May through September, or growing season rainfall in the climate division in South Georgia. And you see that the average is about 23, 24 inches, but we rarely get average. It's usually much above average or much below average. A story related to agriculture in the area, John Beasley, who was a peanut expert with University of Georgia, always said that you need 24 inches of rainfall during the growing season to make a peanut crop. And here in South Georgia, that's what we average, so everything should be good. The problem is you never get that exact 24 inches, sometimes more, sometimes less. And even when you get ample rainfall, it's the temporal distribution is not always ideal. It's late July and August when the plants are maturing and reproducing that water demand is the greatest. So a 10-day or 2-week dry spell during the peak water demand can be just as damaging as a season-long deficit in rainfall. But what can we say about changing rainfall? Well, there's a growing body of evidence that we're seeing more rainfall in extreme events or heavy precipitation events. And these are figures from the U.S. National Assessment, Climate Assessment, that shows that daily rainfall events of 3 inches or more, which most would consider a heavy or extreme rainfall, they're increasing nearly decade by decade since the 1900s. And we're seeing many more of these 3-inch events in the past 2 or 3 decades than we did prior. Over on the right, this isn't evenly distributed across the region. It might even look like some parts of Central Florida are seeing a little less extreme events, but by their nature, there's not a big sample size for these events, so getting robust statistics out of this kind of study is very difficult. But like I say, growing body of evidence that more rainfall is falling in extreme events. A study we helped with at the University of Florida actually showed a very dramatic increase in events of 6 inches or more. So that's something we'll have to deal with going forward as climate change progresses. On the next slide, we'll take a look at the other side of the fence and another one of our climate and weather threats, and that's drought. Similar to the other graphics, on the top left, I have a graph of the Palmer Drought Severity Index averaged over the state of Florida since 1895. And again, you see the tremendous year-to-year variability, but also interesting, it looks like since about 1990, the mid-1990s, perhaps we're having longer and more severe episodes of drought here in the state of Florida. On the bottom left is a graph from the U.S. Drought Monitor that shows the percentage of the state in the various levels of drought over the last 20 years or so. And you can see a very widespread and severe drought in the 2000, 2001, then again 2011 and 2012. And since 2013, we've been relatively drought-free in the state of Florida. So one might say, oh, well, the 2000s and 2010s, maybe that's climate change showing its head. But there might be something else at play. On the next slide, we'll start talking, I'm not going to go into a lot of depth, but start talking about climate variability and the El Nino La Nina cycle. And these are satellite images of sea surface temperature departures from normal during 2 of the major El Nino events of this past century. One is centered in November of 1997, the other July of 2015, when we had these very strong major El Nino events of warming in the equatorial Pacific Ocean. This El Nino phase, it returns every 2 to 7 years. And there's also an opposite phase called La Nina, where that same area of the Pacific actually cools down several degrees Celsius colder than normal. And both of these phases of the Pacific Ocean have pretty dramatic impacts on our seasonal climate. And actually, they're one of the primary tools for having any skill at seasonal climate predictions across North America. And on the next slide, just kind of a conceptual model of how this works, especially during the colder months. The temperatures of the Pacific Ocean, whether you have the warmth and moisture associated with El Nino, can lead to different predominant jet stream configurations. And the top graph shows the average jet stream configuration during El Nino events, where the subtropical jet is the key player, and it brings us excess storminess and rainfall and even cooler temperatures along the southern United States, the northern Gulf Coast, and for sure the peninsula of Florida. The bottom right is the jet stream configuration during the cold phase, or La Nina, where now the polar jet stream takes a more northerly track. The storm track is now up the Mississippi Valley, but the northern Gulf Coast and the peninsula of Florida is actually left warmer and drier throughout the long winter season. So that's kind of our conceptual model. I will say the state of Florida, I would put forth, feels the impacts of this El Nino La Nina cycle greater than any other state in the union. So on the next slide, we'll see how that works together and influences these multi-year droughts that Florida is subject to. And just like the last graph, on the top is the Palmer Drought Severity Index for, again, the North Florida Climate Division. And on the bottom, lined up with the same time frame, is our familiar Nino 3.4 index, where the red peaks are the El Nino phases, the blue dips are the La Nina phases. And you see a very strong correlation between this Palmer drought index and the phase of the Pacific Ocean, the sea surface temperatures, where it's these multi-year La Nina events, like in 2000 through 2002, again 2010 through 2012. These multi-year La Nina events set the stage for multi-year droughts in Florida and other parts of the Southeast. So on the next slide, we'll change gears to another one of the threats on our list, and that's sea level rise. And humans have dealt with sea level rise before, and I'll show you that on the next slide, but we've seen much more drastic sea level rise in the past history of our planet. Going back 22,000 years, we've seen nearly 150 meters of rise as we came out of the last ice age and these tremendous continental ice sheets melted. But I want to call your attention to around 8,000 years ago, we were still experiencing this fairly rapid sea level rise. And on the next slide, here's the human interaction. Archaeologists here at FSU have found artifacts and remains of Native American settlements out on the coastal shelf in 50 to 60 feet of water. So it's evidence that these Native Americans lived along the coast, and as sea level rose, they migrated their settlements inland, keeping up with the rise of sea level. But on the next slide, we'll look at more modern times now, and this shows the different contributions to modern sea level rise, which we've been experiencing for the past 100 years or more. In the dark blue is the contribution from the warming of the oceans. As the oceans warm, the warmer water takes up more volumes, hence we get the steric contribution to sea level rise. And as of now, it's still the primary contributor. You can also see contributions from the melting of continental ice sheets like Antarctica and Greenland and other glaciers. There is no contribution from the melting of sea ice or Arctic sea ice. It's floating on top of water. It's not on land. It has already displaced the ocean which it's sitting on. So on the next slide, we'll take a look at how do we measure or track sea level rise. And we have two main ways to do this. The first is with the network of tide gauges, many of which go back a century or more, where they very accurately measure the relative height of sea level along the coast. There's two major problems with this data set, though. The first one, if you look at the top left, that's the distribution of these tide gauges around the world. And there's many, many more of them in the northern hemisphere, where there's less ocean mass, and very few tide stations in the southern hemisphere, where there's much more ocean mass. So they're not evenly distributed around the Earth. The other major problem is that the vertical motion of the land that these tide gauges are sited on. For example, up in Alaska, we actually see that the relative sea level is falling because the land surface is rising from crustal rebound left over from the retreat of the continental ice sheets. Down in the Gulf of Mexico at Louisiana, they're experiencing subsidence from a lack of sedimentation due to channeling of the Mississippi River and such. So they got tremendous land sinking there, which adds to their local rate of sea level rise. Here in Florida, we don't have a lot of vertical land motion, so our tide gauges are fairly in line with the global average rate of sea level rise. At the bottom, I showed the tide gauge record from Pensacola, Florida, and we see a very steady increase over the last 100 years or so of about 2.3 millimeters per year. You also see some year-to-year variability there too. But that's very similar to the other tide gauges located around the state. On the next slide, here's our other tool for measuring sea level rise, and it's a satellite called an altimeter, which we've had in space since around 1992. And these altimeters very accurately measure the height of the sea surface as they pass over it to within a tolerance of just a few centimeters, which is quite an engineering feat. But this altimeter record shows us something interesting, is that sea level is not rising at the same rate everywhere. We're seeing the greatest rates of sea level rise over in the Western Pacific Ocean, the warm pool, where ocean temperatures are the warmest and the thermocline is the deepest. We're seeing more sea level rise. We see less sea level rise where there's cold water upwelling along the coast of North and South America. So on the next slide, if we put all this together in one graph, we get this beauty from the latest US National Climate Assessment, where you see the black line is the instrumental record from tide gauges, and then there's a light red line imposed on that, which is the satellite record. And then we have a spread of lines for the different scenarios of sea level rise going forward. One thing I will say is there was a lot of debate a decade or so ago about whether the rate of sea level rise was showing any acceleration or not. Well, the latest research looking at both the tide gauge record and the altimeter record have both determined that we are beginning to show an acceleration in these records of sea level. So what that means is these different scenarios in the National Climate Assessment, the lowest one, which is only a foot or so by 2100, is just a continuation of the same rate we're seeing today. And knowing now that we're starting to see some acceleration and that acceleration should continue into the future, we can almost cross that lowest one off the list. Now, the highest scenario is based on RCP 8.5, which is more and more evidence that's not a real realistic scenario for future emissions, so we can maybe take that one off. But the bottom line is there's still a lot of uncertainty on just what the rate of sea level rise will be in the coming century, and also that the higher rates are probably more likely than lower estimates. So on the next slide, we'll take a look at what does this mean. Even if we do luck out and we fall into one of these lower scenarios, that doesn't mean there's still not going to be big problems. I got this graph from Brian McNulty at University of Miami, and it's the tide gauge record from Virginia Key right there on campus. And it's got some really interesting features. It doesn't have a long record, but it's very interesting features. We've all heard about the sunny day flooding that happens during the king tides down in South Florida. Well, this graph illustrates it well. If you take a careful look at that 4-foot mark, prior to 2015, that 4-foot mark was only eclipsed under the influence of a powerful hurricane, when a hurricane track took it close to shore, not necessarily a direct hit, but close enough to shore to get some of the storm surge effect. However, since 2015, that 4-foot mark's been eclipsed nearly yearly, just from normal astronomical or king tides. And 2019 was actually a banner year where they had 4 or 5 events of that magnitude just from the astronomical tide. So Miami's not the only one experiencing this. Lots of other cities along the East and Gulf Coast are, Charleston, South Carolina, Norfolk, Virginia, New Jersey. William Sweet has done, at NOAA, has done a lot of work on the increased frequency of these nuisance or sunny day flooding events. All right, so we'll go ahead to the next slide and take a look at, I believe this is our final threat, and that's the threat of hurricanes and tropical cyclones. So on the next slide, we'll go back a few years to the summer of 2016. And at that time, both the United States and Florida were in an unprecedented hurricane drought. In 2016, a major hurricane, category 3, 4, 5, had not hit the United States in 10 years. And here in the state of Florida, we hadn't had a hurricane landfall of any strength in that same 10-year period. And this graph here just shows the length of hurricane-free days as compared to this latest 10-year period. Well, there's an old saying in baseball that a player will play to the back of his card. And I don't know if we even do baseball cards anymore, but they had the picture of the player on the front, and on the back would be your lifetime statistics, batting average or ERA. And the saying went to show that a player might have slumps or hot streaks during the season, but over the course of 165 games, he'd be close to what his lifetime averages are. And certainly the same goes with hurricane strikes. Beginning in 2016, Hurricane Hermine, which hit the Tallahassee area, broke Florida's hurricane-free streak. Then in 2017, we had Hurricane Harvey, Irma, and Maria all hit United States territories at major hurricane strength. So we quickly caught up and quickly went to our lifetime average there. But let's take a look at trends in hurricanes on the next slide. On the top slide, we're now talking globally, not just the Atlantic Basin. But the top graph shows the yearly number of tropical cyclones that reach tropical storm strength on the bottom line and hurricane strength on the top line. And I'm sorry, I got that backwards. Number of hurricanes is on the bottom, number of tropical storm strength is on the top. And you see that there's year-to-year variability, but pretty much the global number of tropical cyclones is around 90 per year, and there's really been no change in that number. It takes the right conditions, both ocean temperatures and the state of the atmosphere, for a disturbance to develop into a tropical cyclone. And it takes near perfect conditions for that cyclone to strengthen into a major hurricane strength or Category 4 or Category 5. So there's a lot going on that we don't understand, why a vast number of disturbances never develop while others do. And that's ongoing research. So we really can't say, and none of the latest research really indicates that the number of tropical cyclones are going to increase as the planet continues to warm. However, there is growing evidence that the strongest storms and hurricanes are getting stronger, both in the historical record and modeling studies support that the strongest storms could reach a higher maximum strength. On the bottom left is a study from FSU's own Jim Elsner showing that indeed in the historical record, the very strongest storms are getting stronger. Some other things we can say about changes in tropical cyclones is recent studies have shown that the amount of rain from these storms is increasing. A warmer atmosphere can hold more moisture, and so more moisture is available for these tropical rainfall processes. And some of the rainfall totals, the 60-inch totals from Hurricane Harvey in Texas, was attributed to a changing climate. There's also studies that show that hurricane tracks and forward motion may be changing also. A slower forward motion would mean more time for drastic impacts at landfall, but also more potential for a slow-moving storm to drop more rainfall. So those are some of the changes that we are seeing in tropical cyclones and we can anticipate in the future. So we'll go to the next slide. We'll bring our friend El Nino and La Nina back into it. That's one of the biggest indicators of tropical activity in the Atlantic hurricane season. And here's an old study we had done at COAPS where we looked at all hurricane landfalls, or those that hit the United States at hurricane strength, since 1900. and simply broke them down into the three phases of the Pacific, El Nino in the red line, neutral in the green, and La Nina in the blue. And this is a probability of exceedance curves, which shows the likelihood of having 1, 2, 3 or more landfalls in a given season. And what we see, the probability of one landfall is fairly high in all three phases, from 70 to 90% chance of at least one landfall. When we go to two landfalls, we really start to see separation. Two landfalls, there's only a 30% likelihood during the El Nino phase, but there's a 65% likelihood during the La Nina phase. And if we go out to 3 hurricane landfalls or more, very little chance during the El Nino phase, but still around a 40% chance of 3 or more during La Nina. So a very substantial shift in the probabilities or odds of hurricane landfalls. And so on the next slide, with this in mind, oh, I'm sorry, I didn't update this image. This was the NOAA's Atlantic hurricane season forecast that was issued the last week of May. And even at that time, they were anticipating a very active season. Well, that was just updated last week, and now there's like an 85% chance of above normal activity and only a 5% chance of below normal activity. And we're certainly on pace for that in number of storms right now. If Josephine forms in the next day or two, it will be the earliest J-named storms in modern record. The same could be said for the G, H, and I named storms. So we are on record pace as far as number of storms. We're a little bit behind that in accumulated cyclone energy because many of these storms have been very weak and short-lived to this point. So on the next slide, I think that's about all I have. I'm just going to summarize it and kind of what we've observed in the historical record and what we can anticipate from climate change going forward for each of these threats. Again, sea level rise, the global sea level will continue to rise at least the current rate, and more indications that we are seeing an acceleration of that rate. So the likely range is anywhere between 1 and 4 feet by 2100. Temperatures, very likely that the global temperatures and even regional temperatures are going to continue to rise with increasing greenhouse gas concentrations. Florida, maybe a little less than interior North America, just because we're surrounded by the ocean and the Gulf of Mexico. With drought, rising temperature alone can change the water balance equation and lead to more frequent or prolonged droughts, even if seasonal rainfall patterns don't change. But there is a chance that seasonal rainfall patterns might change. We don't have a good handle on it from the climate models, but that would certainly complicate the drought problem. Rainfall, again, a lot of uncertainty on changing annual rainfall or seasonal rainfall patterns, but a lot more growing evidence that we are seeing more rainfall in extreme events. And just to review with hurricanes, the number of hurricanes may not change much, but there is certainly more potential for stronger storms. And storm surge is going to be a problem regardless, just even if hurricane intensities don't change, adding sea level rise on top of storm surge will just exacerbate that threat. And as an example, an extra foot of sea level rise on top of a 20-foot storm surge from a Category 5 storm probably won't make a lot of difference in damage. However, a 2-foot sea level rise on top of a 2 or 3-foot storm surge suddenly takes it from 2 to 3 feet to 4 to 5 feet, and much more potential for damage. So that aspect of hurricane is surely going to be worsened. And also more threats from rainfall and inland flooding. So with that, I think that wraps up my my portion of this. I see I actually went long. It's easier to ramble on when you don't have a live audience in front of you, I found.
Okay, thank you, David. That was a great presentation. And we're going to turn it over to questions now. And so Tracy will unmute everyone. So you will be able to ask a question to David directly if you'd like. Or again, you can write a question in the chat window and I can read those off to David as they come in. So I'm going to pause here for any questions.
Just FYI, I tried to unmute all and it's not working, so I think we're going to have to depend on each individual to unmute themselves. It may actually be asking your permission.
Hi, David. It's Alan Clark. There's a number of things that could be done, I think, as far as predictions concerned, but probably more appropriate to talk to you afterwards or talk to people afterwards.
I'm sorry, could you repeat the question? I'm getting a lot of feedback and echo.
Yeah, David, this is Alan Clark. I just wanted to say that there's a lot of things that we've discovered recently over in the EOS about how things are sequenced with regard to El Nino and La Nina. And from your plot, I think that that will have a big effect on, perhaps have a major effect on the number of wildfires and things like that, the drought that you're experiencing. But, you know, that's a lot of research to do that, so I don't know whether that'll ever happen. But there are some sequences that, you know, I think you might be able to predict in advance. I think the warm water volume in the Pacific Ocean is absolutely key for that to happen. You tend to get a lot of La Ninas following a big El Nino, for example. And we think we know a little bit about that now. The other thing is the business about your last mention about rising sea level. A lot of the sea level fluctuations that you saw on the coast of Florida are actually driven by the interior wind stress curl in the Atlantic. And I guess you know about that from Tony Sturgis and things, but those sea level rises and falls can be substantial. And so your idea that, you know, adding some sea level on top of an already high sea level is important. Some of those things might even be able to be predicted. And we could talk about that too, if you'd like.
Yeah, thank you, Dr. Clark. Those are all great points. We had done some research in the past connecting Florida wildfire occurrence with the El Nino, La Nina phase, and there's definitely a strong correlation. However, in recent years, they're kind of ruining that correlation because Florida is the most active state in the nation as far as doing prescribed burn and controlling fuel loads. So they've introduced a little artificiality into the wildfire time series, but no, there's still a very strong signal. And yeah, with the year-to-year fluctuations in sea level, Andrea Dutton at University of Florida has done a lot of work on that also, and published on even the El Nino phase having an impact on sea level along the east coast of the southeast Florida coast and Atlantic coast. So yeah, there's a lot of work that can be done, and yep, we need to get together when we can and explore some of these avenues.
That would be good.
We have some questions coming in through the chat. I think the first one that I see is from Dr. Will Dewar. Any update on Miami's efforts to harden against sea level rise?
You know, I'm not really up to date on that, other than the headlines I see in the news. I know they're doing multi-million-dollar infrastructure projects to raise streets and overhaul storm drainage and such like that. There was some idea floated out about building a protective wall or something that I saw in the news, but I really didn't follow up with where that was going to be funded or how feasible that actually was.
Yeah, and this is, Emily, I think that was an Army Corps project, and I believe they will be submitting an EIS and public comment period for that particular project, which I believe is a pretty big undertaking.
Yeah.
And there is another question in the chat window from Ron Saff. He asks, when will the lecture be posted on the website? And I believe the answer to that is a couple of days. We usually have these posted within 1 or 2 days, if I'm not mistaken.
You're correct.
Okay. So that will be at the flbrace.org website.
There's also another comment from Jeff Gehring. Sorry about that, Jeff. Enfield, 2001, described AMO influence on Florida rainfall. One of the Florida management districts found stream flow to be influenced by AMO. Are you doing research on AMO influences?
No, I have not done any research on that. I'm familiar with the study. David Enfield and in partnership with South Florida Water Management District did find that connection between stream flows, especially inflows into Lake Okeechobee, and the AMO. Whether there's some seasonal predictability there or not, I'm not sure.
Okay, and so Ron Sapp has another question. Tampa and Miami are predicted to be ground zeros for sea level rise. What about other cities like Fort Lauderdale or Jacksonville? Will they be much better or off, or pretty much in the same level of severity in terms of sea level rise?
You know, that's a good question. It all depends on how much property and value is located in the vulnerable low-lying areas. But sure, no part of the Florida or United States coast is going to be immune to the impacts of sea level rise. And I know there are neighborhoods in the greater Jacksonville area that suffered pretty badly after Hurricane Irma, where levels on the St. Johns River remained elevated several feet for a number of months. So there are vulnerable areas in these other cities. Tampa's got a lot of low-lying areas, so that's why they're one of the poster children, if you will. But no, any coastal community is going to be facing the same issues, I would think.
Okay, we have a couple more minutes if anyone else has a question. And David, I think, so I have one I can ask. Can you explain or provide a reason that nighttime minimum temperatures have been warming more than the daytime maximum temperatures?
Yeah, that's a very good question, and I think there's 4 main mechanisms at play here. Now, which ones are the dominant, I'm not sure, but the first mechanism is the background climate is changing. The entire global atmosphere is warming, has warmed about 1 degree Celsius over the last 100 years. So the background climate is changing. And as part of that, sea surface temperatures are also warming. So warmer sea surface temperatures surrounding the state would contribute to warmer nighttime temperatures. Land use changes, including urban heat island effect, but other land use changes like draining of wetlands and widespread use of irrigation can influence temperatures, and they are felt more strongly at nighttime also when the atmosphere is more stratified, less mixing, shallower boundary layer. These changes in land use are seen in surface observations more at night than during the daytime. And also with the changing background climate, we are also seeing an increase in humidity, and a moister atmosphere does not radiate out heat as efficiently as a drier atmosphere. So a more moist atmosphere will lead to elevated nighttime temperatures. So I think it's a combination of all of those factors is why we're seeing more warming in the overnight minimum temperatures than in the daytime high temperatures. And in fact, across the state, over the last 5 years, the number of record warm nights more than doubles the number of record warm days.
Okay, and I think we have a good follow-up question to that. The question is, does the overnight temperature increase affect the water footprint of peanuts, so peanut crops?
It's a good question. I'm not sure I know the answer to that. I'm not a plant physiologist. It might actually have the opposite effect as the warm overnight temperatures affect plant growth and reproduction. They might not be as efficient in using water as a healthy plant. So I really don't know. I'm just conjecture there.
Okay, thanks. I don't see any more questions in the chat window. Are there any final questions for David? And we are at the top of the hour, so I guess this is a good time to wrap up. Thanks again to David for the great presentation and great information and discussion today. If you end up having a question that we did not answer, that you did not submit, either put it in the chat window now and we can follow up with you, or you can follow up with one of us directly. And as a reminder, this recording will be available on the Florida Brace website in the next couple of days. And we hope to see you all at our next webinar. So keep an eye out for that announcement coming in the next couple of weeks, most likely. So thank you, everyone. And thanks, David. And we hope to see you next time.